In this lesson, we're going to discover what is meant by gravitational potential energy, learn the equation, and how to apply it to problems. Let's begin then by having a look at the work done in lifting a body. You've already met the work done in moving a body along the floor. So if you look at that block, mass m, in the diagram, if you were to apply a force horizontally to it and move it a certain distance, the work done would be the applied force times the distance moved. You should already be fairly secure with this before proceeding. Now let's try and work out the work done in lifting this body vertically upwards. Well, if we're going to lift this body upwards, we're going to have to apply a force to it pointing up the way. So in the next diagram, you can see my applied force lifting the body up the way. So if you were picking up a bag, that applied force would be exerted by your hand. Now, of course, that's not the only force on the body. The body also has weight mg, which, as you know, always points vertically downwards. Now, in all of our problems, we are going to assume that when you lift this body, you're moving it upwards with a uniform or constant speed. If we lift the body up with a uniform speed, Newton's first law tells us that the forces on it must be balanced. Balanced forces produce uniform speed in a straight line. What does that tell us? That tells us that if we move this body up with a uniform speed, the applied force, F, must equal in size the weight mg. That tells us then that whenever we lift a body upwards with a uniform speed, what force do we need to do it? It's just the same as the weight in newtons, whatever that force is. Be aware that we're ignoring any small accelerations required to get the body moving in the first place. Very often people get a little bit hung up on that. Obviously, we've got to take the body from rest to moving at this uniform speed, but that happens quite quickly, and we're going to ignore that tiny bit of the motion. As far as we're concerned, the entire motion is a nice uniform speed with balanced forces. Let's imagine then that we are going to lift this body up through a height h. In physics, whenever we talk about a distance moved up or down, we call it a height. It's really just a distance in the vertical. So we're going to call it height h. So the body starts off on the floor, as you can see, and it ends up at a height h above the floor. So here we are, our body has been lifted up a height h. Well, I hope you remember that when you lift a body upwards, it gains gravitational potential energy. We know that because if we let it go again, it falls downwards and gains kinetic energy. So where does that kinetic energy come from? It had to be stored somewhere, and it's stored as gravitational potential energy. So a really important idea is this. The work done in lifting the body always equals the gravitational potential energy gained. So if I were to do 10 joules of work in lifting a body up, that 10 joules will be stored as gravitational potential energy. I know it's stored because if I let the body fall, that gravitational potential energy comes back out again as kinetic. This idea, work done in lifting a body equals gravitational potential energy gained, is very important in this part of the course, and you should memorize that word equation. You'll find it very helpful if you can memorize that. Okay, let's get some symbolic equations down from these word equations. Well, the work done in moving anything is always the applied force times the distance moved. So the left-hand side of the equation is force times distance. the right-hand side of the equation, well, the symbol for gravitational potential energy is E subscript P. Our next line allows us to replace the applied force with mg, the weight, because we established earlier on that the force required to lift the body is just the same size as the weight, assuming uniform velocity, of course, uniform speed. The distance, well, that's just h, height. Height is simply the word we use when the distance is up or down. So we have mg times h equals EP. If we rearrange that equation to make EP the subject of the formula, we get that gravitational potential energy gained EP is mgh. And that is the equation for gravitational potential energy. If the mass is in kilograms, g is the gravitational field strength, which on Earth is 9.8 newtons per kilogram. The height is in meters, then the gravitational potential energy gained will be in joules. That equation is on the list. Okay, I can sense you want a worked example, so let's do one. Okay, so Tiernan, being a strong chap, lifts a school bag of mass 6 kilograms, a height of 1.4 meters from the floor into his locker. That's quite a high locker, but he's a strong guy. Now, question is, how much gravitational potential energy has the bag gained during this lifting? And secondly, how much work has Tiernan done in lifting the bag? Now, before you look at the solution to this, which is coming up shortly, pause the video and work out the answers on paper before seeing the solutions. So do this now. Well, the solution to part A requires us to list our variables. So you read through the question and you identify all the physics quantities mentioned. So what have we got here? Well, we're asked for the gravitational potential energy, so EP has to be listed. The body has a mass, so m is involved. The height raised is involved, h. And that should be triggering in as a knowledge of the equation EP is mgh, so we need to list g as well. So let's fill in all the quantities we know. We don't know EP yet, that's the question mark. The mass is 6 kilograms. G on Earth is 9.8 newtons per kilogram. You should always assume we're on Earth unless told otherwise. And the height is 1.4 meters. Okay, the next stage then, we've listed our variables, is to state the equation. EP is mgh. Hopefully you'll know that from memory, but it is on the equation list. Substitute in the values for m, g, and h. Use your calculator to get the final answer, which is EP is 82.3 joules. So Tiernan has done 82.3 joules of work in lifting this bag. Part B, how much work has he done? Well, in many ways I've just told you the answer to that. The gravitational potential energy gained was 82.3 joules. It follows then that Tiernan did 82.3 joules of work in lifting the bag, because all of the work that he did meant that he transferred energy to the bag. So every joule of work he did became a joule of gravitational potential energy. So the answer simply is that during the lifting process, Tiernan did work which became gravitational potential energy gained, and so the answer is simply 82.3 joules. So the gravitational potential energy gained by a body in being lifted will always be the same as the work done by the agent doing the lifting. And that's gravitational potential energy.